Today I will make a model for biomass combustion in Aspen Plus. Before starting, I just tell you that I assume that you already know a little bit about Aspen Plus, so I am not telling you about basics and what to do in Aspen Plus. If you want to know about basics, there are other videos available on YouTube. And in this video I will making combustion model for biomass, and the idea is to make model which is flexible enough. So by flexible I means that we can change fuel amount or air amount in stream, and it will automatically calculate exhaust gas temperature accordingly, and also tell us how much heat is available in exhaust gases or flue gases from biomass combustion. For this video I am not making the heat recovery steam generation section, but I will only show that how you can estimate the amount of steam required or amount of steam that can be produced from combustion of biomass for specific mass flow rate. You start from here and use new file, which I already did, and you need to add components. We are starting with biomass, and biomass is not already present in Aspen Plus properties database, so we add it as a non-conventional component. And biomass already have ash, which will also be non-conventional. Then we have carbon, hydrogen. These are elements which are present in biomass, which we will mention in the simulation page. Then we have nitrogen, chlorine as Cl2, sulfur, oxygen, and then when we combust biomass, it will produce water, and water will also be present in biomass as a moisture content. CO2 will also be produced from biomass combustion. Similarly, SO2, SO3, as sulfur is present. NOx will also be produced, and ammonia will also be there, and HCl will be formed from chlorine. I think these are enough, and we can change it later also. For methods, Aspen Plus calculates only heat and enthalpy and density for biomass, and there for enthalpy you need to use H-Colgen, and for density you need to use D-Colgate. If you know about the enthalpy of biomass, you can also mention it, which I will show you later, but here we will see how it will be estimated by Aspen Plus. Similarly, you need to mention about other non-conventional component, that is ash, and we'll use same properties. And methods, we will start with Peng-Robinson, and then binary interaction, you just click it and it will be blue. Your required properties input is complete. Now we can go to the simulation environment. We'll start with biomass stream, and before starting we can just set up with stream class, and you see stream class is only mixed, so you need to add non-conventional also in the stream class. And units, I am not touching it, we can just go with existing unit setup. Temperature degree C, 25, pressure 1 bar will be enough. And you can change, sorry, I am changing it in mixed, I need to change in non-conventional one. So because biomass is non-conventional, 25, 1 bar. And you can add mass flow rate here or here, but I always do it here because it's easy to change it, and here I will convert it as mass fraction. This stream will be whole biomass, so put it here. And mass, I am using it as a kilogram per second, let's say 20 kilogram per second. And then you see this is red, so you need to add approximate, ultimate, and sulfate analysis. With approximate, for example, let's assume biomass has a moisture of 40% fixed carbon 45, volatile matter 40, and ash 15%. Ultimate analysis, you can mention whichever you have values. I'm using built-in values from my old project: 15, 52.9, 7.3, 1.3 for nitrogen, chlorine is 0.5, sulfur is 1.1, oxygen is 21.9. One thing to note that ultimate analysis is moisture free basis, so if you add all this it should be 100. And sulfate is not really useful in our simulation, but you can put it if you have some values. Sorry, it's 0.03 and 0.135. Now you see everything is blue, so our stream is completed, and there are two reactors that will be used for biomass combustion. One reactor we will be using R yield, which is decomposing biomass into its constituent elements: carbon, hydrogen, nitrogen, chlorine, sulfur, oxygen, moisture, and ash, etc. We name it as a decompose. And then we will connect stream with that reactor, and we need the output. We will say intermediate biomass stream. Temperature we will put it same, and pressure 1 bar also, no pressure drop there. And there you need to mention about component yields. So R yield works, I assume you already know. You need to mention about all the components and their yield manually. So in water, so biomass will have ash, carbon, hydrogen, nitrogen, chlorine, sulfur, oxygen, and water. And we are using mass basis. And in the beginning I mentioned that I want to make the model flexible, so if we change different composition, I want to change it accordingly automatically. You can do it, you can put the actual values based on your stream, but we are changing it through calculator block. So we are adding it some random values, let's say 0.1 for all of it, and which we will change it through calculator block. You can run it now also, but it will give you warning and error that the reactor is not in mass balance. So to make it, we will go to the calculator block, and we will name it. Okay, it's already there, so let's say yield reactor. And from here we will be changing, we are taking biomass stream as an input, we are importing it, and then we are exporting the yield through calculator block to the yield reactor. And for this you need two variables: ultimate analysis, which we will be importing, and it will be compat our vector. Stream is biomass, it's a non-conventional stream. Component is biomass. Attribute is ultimate analysis, yes. And then you need water. This will also be imported, and here we are only importing variable. We don't need to import the whole proximate analysis. Component will be biomass, attribute will be proximate analysis, element will be 1, because if you remember, you can go to the biomass stream. moisture was the first element. So if you use 2, it means you are using fixed carbon variable. 3 for volatile matter and 4 for ash. We are using 1, so it will be moisture. And then you need to add other variables, for example ash, which we will be exporting to the yield reactor. Block variable, decomp is a reactor, and we will be importing mass yield. Ash id2 will be non-conventional. And you need to make sure a variable doesn't mean that you are using the same thing. If you use here as carbon, it will value will go to the carbon, so you need to make sure that you are using the right ID there also with respect to the name. And similarly we will make other variables. As for carb, again we will be exporting it. Block variable, mass yield, carbon, mixed. And similarly you need to do everything for hydrogen, nitrogen, chlorine, sulfur and oxygen. I will do it very quickly to save some time. So you will do it for carbon, hydrogen, chlorine and sulfur, and with oxygen when I am doing it I see some discrepancies. So I think we added O as a component, oxygen monatomic gas, we need O2, so we go to the properties and change O to O2. So yes, now it's oxygen. You need to do the binary interaction thing, just clicking it and go to the simulation back, and here it will be O2, oxygen, it will be big. So that's what I was saying it earlier. You need to make sure what you are doing here. It's in these kind of simulation tools, it's always garbage in, garbage out, so you need to make sure that you're putting right amount of information in there. You need to type this code which is already present in one of the example in solids processing in Aspen Plus. So I'm just doing it to save my time. It is based on Fortran language, so you need to make sure that all the code where the calculations are being done are written in column 7, and C means comment, it does not execute anything. I think why it's not blue yet, maybe, yep, it's column 6. We need to go to the column 7. Here it will show at which column it's present. Yes, now it's blue. So how it works, because as I mentioned in the biomass ultimate analysis is present as moisture free composition, so you need to add moisture in the yield. So we import moisture first and we convert it as a factor. 100 minus water is the moisture from biomass, which is 40%, so it will be, water will be 40% as it is in the yield reactor, and rest will be converted into with respective values. For example, ash was 15%, so it will be multiplied with 0.6. So 100 minus 40 over 100 is equal to 60 over 100.6. Similarly, carbon was, I guess, 52%, so 52.9 into 0.6, etc., and similarly everything. And yes, and we go to the reactor and we need to change, I guess oxygen was removed and now it will be oxygen there, and we can run it. And model has been run and it's giving some warnings and errors, so we can just go to the first, start one by one how to remove the errors, we can go to the reactor calculator block input, and we can see the results, and we see the value red was fine. Ultimate analysis: ash, carbon, hydrogen, nitrogen, etc., oxygen and water, and value written was ash instead of 0.1, now it's 0.09, carbon instead of 52.1 is 0.31, but there is no moisture here, so I guess we did not added the moisture there, this H2O in as a yield. So we add another variable H2O. Again we will be exporting this block variable to the reactor. Mass yield ID1 will be water and mixed. It's better to reset everything and then run it. Yes, now warnings are complete, but there are errors. We'll see what are the errors. First go to the reactor calculator block, and now we can see if all the variables are fine. Yes, water is now instead of 0.1 it's 0.4, and similarly with oxygen. We will change these values later also in stream biomass stream to see how it will be impacted, but let's go to the reactor and see what are the errors. It is saying that component attribute ultimate analysis is missing for ash component, and similarly for sulfate and proximate analysis. Because we mentioned that we have one ash component there which is non-conventional, so we need to add its attribute. So stream ID NC, it will be ash, and we will be adding proximate analysis. Here it will have 0 moisture, we can skip everything. For ultimate analysis it will be 100% ash, and we will remove we will just don't do anything with other. Similarly with sulfate we can just say it will have 0 organic, and then we can again reset it and start or run the simulation. See, now it runs with no errors and no warnings were issued during simulation. So this is complete, and we can add other reactor for combustion. So because you can see into stream results, here mass fractions, so it was biomass at all, but now biomass is decomposed into ash, carbon, hydrogen and respective elements. And now we need air and other reactor. We can use R stoic or R Gibbs. Let's go with R Gibbs. We name it as combustion reactor. Join the stream with that reactor and then add air also, and this will be flow gas. I will name flow gas 01. It was not linked, so we need to join with that also. With air also you can mention mass flow rate for oxygen and nitrogen, but it's better to put as a mole fractions. For simplicity I'm only using nitrogen and oxygen, but it will have moisture also in reality. So temperature is, let's start with 25. Normally air is preheated while entering into the boiler, but just for the simplicity, and mass flow rate in kilogram per second, let's use 150, and There you can have pressure at around 1 bar, and instead of temperature we use adiabatic reactor 0. And now you can run the simulation again. Yes, it's better to reinitialize and then run it to avoid any errors. And you can see the temperature is very high, around 1600 degrees Celsius. Normally it will be around 1000. So you need to make changes, that what is the exact amount of air required, and what is the exact amount of air composition. Normally there is flow gas recirculation also there, and some moisture has also been added there. So these are some changes in reality, but for simulation purpose it is fine. You can also do some changes here, also put some moisture there as 5%, oxygen 2%, and nitrogen 75%. Or you can also calculate amount of air required, or what is the amount of air should be present in the flow gases. For example, let's say there is 10% oxygen that should be present as a mole fraction in the flow gases. That you can do it from here. Go to design specification. We use variable O2. It will be mole fraction, in which stream flow gas 01 stream, and which component oxygen. So O2 should be present as 0.1, target 0.1, and tolerance is, let's see, 0.001. You can change it accordingly. And what you want to vary amount of air. So here go to stream variable and go to air, and mixed variable is mass flow, and in kilogram per second. Just avoid using mass flow rate here directly, because if you are using mass flow rate directly here, then you need to mention which component, then it won't be right. So here is better to start with stream variable and go with mass flow in kilogram per second. Let's start with 1 and go a little bit 1000, lower and upper thing. And there also, instead of directly mole fraction, you can go to the stream variable, and which variable, then you can mention it, mole flow or everything. So there I was using mole fraction directly because I am dealing with only one component. So if you are dealing with whole streams, it's better to go with stream variable. Then I am resetting it again. Model has been simulated, again no errors. And now, so you see the temperature is fine, like 1200 degrees Celsius, and you can just see by double clicking it, amount of oxygen was fine or not. Mass fraction, sorry, we will dealing with mole fraction. Yes, mole fraction is 0.1. So we can go to the design specification and go to its results, and it is like initial value of air was 540,000 or 540 tons per hour. Now it's 766 tons per hour. Or we can see how much was it in kilogram per second. So we put it as 150 kilogram per second, but if you go to the results, it will be, let's change it to kilogram per second, 212 kilogram per second. And then also you can play differently with design specification. So for example, if you really want to control the temperature here, instead of using oxygen mole fraction, you can mention temperature of flue gases. I am deactivating it, and I am using DS2, where I am changing amount of air to maintain temperature. You want to maintain temperature of stream, which stream? And go for stream variable, flue gas 01, mixed variable is temperature, and the specification is temperature. Target value is, for example, 950, and your tolerance is 10 degrees Celsius. And then again you want to vary amount of oxygen, stream variable, air, mixed variable, mass flow 1 to 100. Just see you're using right unit. Kilogram per hour is very less in terms of thousand, so kilogram per second. Again I am resetting it, and now I deactivated first design specification, so it will only use this one. But if you activate both of it, then Aspen Plus will give errors, and because you are changing one variable by changing using two design specifications. So model has been simulated, and you see temperature is now 941, and we can see amount of air it required to achieve that temperature. Very high amount of air, 298 kilogram per second. So these are just a small things you can do, and you can see how much is the stoichiometry amount of air required, that you can also do with calculator block. So if you need me to do it, I will do it also in some other exercise, but instead of this, now we can check how much heat is available in flue gases. So you can use a simple heat exchanger. Use X1, connect flue gas 01 stream here, and then 02. Normally cool it down to 130 degrees Celsius. Pressure drop, I will just say 1 bar. Again I'm resetting it and then running it. After simulation we can check amount of heat. It will present in calorie per second. We want in megawatt, so you can change the units there, but let's see. Go to the results, and there, instead of, we can just do it here. Yes, 307 megawatt. Accordingly, and you can mention it is based on the amount of heating value which has been calculated by Aspen, but you can change the heating value manually also. There you need to mention for enthalpy instead of 1.6 there, and then you need to go to the pure components, go to non-conventional, name is as heat, go to H combustion instead to use megajoules per kilogram for biomass, and use value, let's assume 15. Go to simulation. Now it will use 15 as a heating value, and then let's see if we see some changes or not. No, there was not any much changes from there also, so that is fine. So, and for example, if we change biomass flow rate from 20 to, let's assume, 15, and moisture from 40 to 20, and then run it. Yes, model has been completed, and it has been giving us similar values, I guess, basically because we reduce the moisture content and it does not translate there. So let's see, moisture is again 40 and amount of biomass is less. Yes, now it will be less amount of megawatts available. $239 instead of 300. So that's what I was telling about the flexibility thing. So try to make models accordingly, use calculator block, design specification block a lot to see to make changes accordingly. So, and in this model, like, I can change ultimate analysis. I do not need to do anything there also. In decompose or yield reactor, it will give me results accordingly. And also it's better to check how much air is required and how much flue gas is being circulated back there also. So to control temperature, we can make the model more complex later also. And you can also check how much steam you can produce from this heat available. Easy ways to use another heat exchanger here. I call it HRSG, simplest one, and it will take heat from flue gases, put everything there, put heat in, and then there will be heat out, which will be 0 if I use no heat losses. And then use material, for example this, water in, feed water in, and steam out. Water will be water, so go for mole fraction or mass fraction, whichever you like. 1. Temperature will be, let's see, water is coming back at 105 degrees Celsius and 70 bar from steam turbine, and just give any mass flow rate in kilogram per second. Let's assume 1 there. It will be changed by a design specification block. And you need steam at, let's see, 4 or 500 degrees Celsius and 70 bar also. So let's assume 0 pressure drop, or you can use 74 bar there, and 4 bar will be pressure drop in heat recovery steam generation. You need to have another design specification block, name it as a steam calc, And there what you want to need to change, maintain, you want to maintain heat out, which will be heat duty, so you want to use heat out 0. Tolerance is 0.001, and you want to vary the mass flow rate of water. Stream variable, stream will be water in, substream will be mixed, variable will be mass flow rate, kilogram per second. Just make sure that you are giving it enough variable limit, lower and upper threshold. The main thing is, like, you can play a lot with this design specification and calculator block, and it will give you so much opportunity to make your model flexible. Yes, and model has been simulated. You can see the results. So it will, initial value was 1 kilogram per second or 3600 kilogram per hour, so it will be around 284,463 kilogram per hour or 284 tons per hour of steam. And it's taking all the, by taking all the heat, or you can just check it in kilogram per second there also by changing the unit to SI. S3 79 kilogram per second of steam can be produced, and then you can just expand it in steam turbine and see how much power it can produce, and play it with it. If the video has been becoming too long, so I will just finish it here, and if you have any questions or confusion, then just write it in comments and then I will answer it accordingly. And see you in next video.